Applications of op-amp. We have many applications related to operational amplifier. Adders, subtractors we have, and we have filters. Different types of filters can be designed using this op-amp. So one of the example here we have is adder or summer amplifier, where different input signals here given in the figure 1 we have V1, V2 and so on up to Vn are added, and we get at the output V0 the sum, that is addition of all these input voltages at the output V0. So this is linear addition will takes place here of all the input signals applied. Here we have a virtual ground at node A. The meaning of virtual ground is here it is assumed the inverting terminal minus terminal of this is at ground potential, that is virtual ground in case of operational amplifier. So if you apply KCL at node A, the total current approaching to the node A is I. Here we can see the total current I which is approaching at node I, which is the sum of the individual currents flowing through R1, R2 and so on Rn. These are the individual currents. So sum of all these, algebraic sum of these currents is equal to I. From KCL we can get that. And next, if you consider the voltage difference between the node A and the output voltage V0, which is nothing but VA minus V0 is equal to the current flowing through RF into I. So that is VA minus V0 is equal to RF into I. If we consider the voltage VA is equal to 0 here, then we get V0 is equal to minus RF into I. And in place of I we can substitute this V1 by R1 and so on Vn by R1, that is we got from KCL. And if you simplify this, and we get this equation minus of V1 into Rf by R1, where Rf is the feedback resistance taken from output to the input. And suppose if you assume or we take all the resistances R1 equal to R2 is equal to and so on Rn is equal to R, then we get the output voltage V0 is equal to minus Rf by R into sum of the all the individual voltages. So that is how we get addition of individual voltages here, and the output here is proportional to the sum of individual inputs, where we can take the gain, I mean AV1 with respect to R1 resistance is minus Rf by R1, AV2 minus Rf by R2 with respect to R2 resistance, like up to AVN is equal to minus Rf by Rn. So if you replace this minus Rf by R1 into V1 is equal to AV1, like that for V2 and so on Vn, we get this equation V0 is equal to V1 into AV1 plus V2 into AV2 and so on Vn into AVN, where AVN, AV2 are the individual gains of the inputs, where we have AV1, AV2 and so on AVN are equal weight configurations. Here it is, they are equal weight configurations. The summing amplifier can be used as a level shifter for any AC signal, that is it is used to shift the level of the voltage. That is, for example, if we want to shift, if we have an AC signal, we want to shift the level, we can add a DC signal to that. That is, for example, if you have an AC signal with plus 1 and minus 1 volts, we want to shift this, the voltage of this we want to shift, so we can add some DC to this. So we have number of inputs we can apply to the op-amp, like we have seen earlier, V1, V2, V and up to Vn. So for example, V1 we apply AC and V2 we apply DC signal. So these two will be added. For example, if you want to add some 2 volts DC to this signal. This is AC signal which is having equal amplitudes above 0 and below 0, plus and minus. So this is V1 we take, this we can take V2, and suppose this is we take as 3 volts. When we add this 3 plus 3 to this minus 1 and plus 3 to this will be shift, the below 0 cycle will shift above 0, because minus 1 plus 3 it will be 2 and plus 1 plus 3 it will be 4. So it will shift to above 0 and we get the signal above the 0 level, that is around plus 2 and 4 volts. So when we take this 0 volts, and here we are going to have 2 volts and here you are going to have 1 plus 3 4 volts. So what happened here, the AC signal has shifted above zeros, that is adding a DC, which is called as offset DC, and added. So theoretically individual gain controls may be produced by making the input resistors variable. If the input resistors R1, R2 and so on, we can make them variable. At the feedback resistance also, RF, which we have one feedback resistance, that also we can vary by using potentiometer. So AC signal of different frequency and phase relationship do not add correctly. Whatever we seen earlier in this lecture, that is related to the signals, DC signals we can add, but when we consider all the signals are AC, it is not exactly possible to have this type of addition. In that case, we take RMS values will be considered and those will be added. RMS, root mean square values of the AC signals will be considered in addition. So that is about adder using op amp. Next we have subtractor. Using this op amp we have subtractor, where we take V1 and V2. To understand the operation, we take only two signals here, V1 and V2, and finally we get the output result will be difference of these two signals, V0. Here we can see, here we have V0 is equal to V2 minus V1, which is the difference between the input voltages V1 and V2. So we can have number of inputs. Here it is taken only two inputs, V1 and V2, and we can get the difference. If suppose we take V1 equal to 0, that is V1 is grounded, then V0 will be equal to just V2. The circuit shown becomes now the non-inverting amplifier it becomes, because here we are taking V1 is equal to 0. The V0 which we have the equation is V2 minus V1. Suppose if we apply V1 is equal to 0, then V0 finally we get V2 minus 0, that is going to be V2. Since we are getting positive voltage at the output, this is called as non-inverting amplifier. It becomes as non-inverting amplifier here. Okay, unity gain we can have with the input voltage V2 by 2, also we can take half of the V2 voltage at the non-inverting terminal. Then we get the input terminal voltage, if it is V2 by 2 we apply, and the output voltage V0 will be is equal to V2 by 2 and 1 plus RF by R. This equation we can use. This is nothing but we get the voltage. So similarly, if V2 is equal to 0, V2 is equal to 0, then the output voltage V0 will be V1. Now the circuit becomes as inverting amplifier with unity gain, and the output voltage is given by V0 is equal to minus V1. So we get this inverting and non-inverting voltages we get. Here we get V0 is equal to minus V1 we get. And overall, if we consider two voltages V1 and V2, the difference voltage V2 minus V1 will be V0. So V0 is proportional to difference between the two input voltages. So that is how we can have the sum adder circuit and subtractor circuit using operational amplifier. And here we have an example problem. We have an example from problem. Here it is V1, V2, V3 individual voltages are applied at non-inverting terminal. The plus terminal is called as non-inverting and minus terminal is called as inverting terminal. The given problem here it is with the RF resistance 10 kilo ohms, and we need to calculate what is V naught. V naught here it is calculated by using superposition theorem. Individual voltages, first we consider V1, and during that we consider V1, V2 and V3 are considered to be zeros, and we will calculate the voltage with respect to V1. What will be the voltage we get with respect to V1, that is V and I, non-inverting terminal voltage, that is voltage at node B, will be calculated. That is calculated by considering the V2 and V3 voltages both will be zeros. So V2, V3 0 means we have this equivalent circuit, that is R1. Here we have considered R1, R2, R3 as R's only. So this both will be R resistors here, this one, and this V2 and V3 are considered 0, so that just acts as short circuit. So we have here this R and R are these two R's, and these two are having the common ground, so we have taken the common ground here, and R and R are taken in parallel, R into R by R plus R, so we get R by 2. And this we are calculating here the voltage VB, which is called as non-inverting voltage, the voltage at the non-inverting terminal. So here we have the voltage 2V is divided between this series R and R by 2. So we use the formula here. The voltage at the node B is at the non-inverting terminal, that is only with respect to 2V volts, V2 and V3 are zeros. So non-inverting voltage at B is, we have here voltage divide rule between two series resistances. We are calculating the voltage across R by 2, that is parallel combination of R and R. So we get 2 volts is divided across R by 2 and R. We want to have the voltage across R by 2. So 2 volts into R by 2 by R plus R by 2. If you simplify this, take the LCM in the denominator, we get 2R plus R. 2 from the numerator and denominator will get cancelled, and we finally left with 2 by 3 volts. So this is with respect to 2 volts only. Now same way we consider another voltage V2 and we calculate the non-inverting voltage at the node B with respect to V2. During that time V2 is 3 volts, V1 and V3 are considered to be zeros. And same way we calculate the voltage due to 3 volts, R by 2 into 3 by R plus R by 2. So if you simplify this, we get it as 1 volt. Same way we calculate with respect to V3 equal to 4 volts. During that V1, V2 are equal to 0. And here 4 into R by 2 by R plus R by 2, we get it as 4 by 3 volts. We get it as 4 by 3 volts here we get. So we can calculate the voltages with respect to V1, V2, V3 at node B individually using superposition theorem. And by considering the virtual ground concept of op amp, VA here we get is equal to VB. VA is equal to, that is the voltage at node A, VA is equal to the voltage at B, VB, both are same. Now we have the voltage VA is equal to V naught into 5 kilo ohms by 5K plus 10K, that is the voltage V naught is divided between 10 kilo ohms and 5 kilo ohms, and we want to have VA, which is the voltage across 5 kilo ohms. The voltage across 5 kilo ohms is nothing but VA. So V naught is divided between 10 kilo ohms and 5 kilo ohms. Here we take. So VA is nothing but the voltage which is divided between two series resistors, that is 5 kilo ohms and 10 kilo ohms, is V naught, and we want to have the voltage across 5 kilo ohms. So V naught into 5k by total resistance 5k plus 10k, 10 kilo ohms. So what we get here is VA is equal to V naught into 5 kilo ohms by 15 kilo ohms. We get, kilo ohms will get cancelled, we get V naught by 3. So VA we get it as V naught by 3, and due to virtual ground here we can consider that is VA is equal to VB. And finally we want V naught voltage, that is with respect to three voltages, that is V1 we have, V2 we have, V3. So after calculating these voltages at the non-inverting terminals, non-inverting terminal B, because of V1 we got 2 by 3 V, because of V2 we got 1 volt, because of V3 we got 4 by 3 volts. Using superposition we got the voltages at node B because of individual. Now we will be calculating what will be the output voltage V naught at output terminal because of these individual voltages. So first we take it as with respect to V naught, that is with respect to 2 volts, V naught of 2 volts we get 1 plus Rf by R into with respect to V naught of 3 volts and with respect to V naught of 4 volts. So if you add these three voltages, and first one we can see here V naught with respect to 2 volts is nothing but 1 plus Rf by R into 2 by 3. This is with respect to V naught of 2 volts. 2 volts. Same way we get with respect to V naught of 3 volts is same 1 plus Rf by R. This is with respect to feedback resistance we have into 1. This 1 volt is nothing but with respect to the V2 voltage at node B. So this equation, so for all the three V naught individual voltages with respect to 2 volts, 3 volts and 4 volts, we are going to have 1 plus Rf by 2 by 3, 1 plus Rf by 1, and with respect to 4 volts also 1 plus Rf by R into 4 by 3 volts. So we take 1 plus Rf by R common into 2 by 3 plus 1 plus 4 by 3. If we take the LCM here, and Rf and R values are given already, we take the values, Rf is 10 kilo ohms and R is 5 kilo ohms. We substitute and simplify. Finally we get the V naught voltage is equal to 9 volts. Okay. Thank you for watching. Next class we will continue the integrator operation.